The main problems that we're dealing with now have to do with improving the sophistication of the types of attacks that we can deal with, such as active interposer attackers and supply chain attackers and more types of firmware bugs, and then kind of our big ticket item is post-quantum cryptography. The new algorithms coming out with the NIST standards and other standards happening around the world.
Right now, what we're working on is allowing TPMs to take advantage of attestation that depends on the version of the firmware, so that you can recover TPM firmware in the field and things like that. Looking forward, we're thinking about things like post-quantum cryptography applications and things like that, because we know that's coming in 10, 15 years, and it's going to take time for the industry and the hardware to get to the point where they can do post-quantum cryptography fast enough to matter. So we need, I expect we'll see substantial hardware changes in the TPM to support that, over the coming years.
So from its inception, TPM 2.0 had algorithm agility as a main focus of the design. So in a number of ways, post-quantum is sort of just another evolution on the road of supporting more and more types of algorithms that look more or less the same as the ones that we've had before. So the two main post-quantum attacks that we're aware of today, one of them is called Grover's algorithm, and it's a symmetric key attack. And basically the way that we can respond to Grover's algorithm is by using larger keys and larger hashes and all getting some sleep. So that's sort of the easy version of our task. The harder problem to solve in the post-quantum cryptography space is going to be something called Shor's algorithm, which allows some of the most common asymmetric cryptography primitives that are in use today to be more or less easily broken by sophisticated enough quantum computers. And every year, the most sophisticated quantum computer gets a little more sophisticated, and the most sophisticated theoretical attack using a quantum computer gets a little easier. So at some point, we expect the most advanced computer to be able to run the most advanced algorithm and actually break algorithms that are in use today. So in response to this, NIST has run a series of competitions. They're about to standardize the first winners of these competitions that define a whole set of new algorithms. And they don't work exactly the same way as the ones that we're used to. So we have to update the standard to make some sense of the new ways that the new algorithms work. For folks who are familiar with the embedded hardware security space, cryptography is hard, hardware is hard, embedded is hard. We get to do all the hard things all at the same time. And so we have to deal with some of the more limiting constraints of the capabilities of hardware, how much working memory they have, how much storage they have, how powerful their processors are. We have to apply these same limitations to a bit more sophisticated algorithms than what we're used to. And so planning in advance for the ability to use these new algorithms in the hardware that's going to come out over the next 5, 10, 15 years is sort of what's on the top of my mind, because the current estimated timeline for post-quantum cryptography's relevance to cryptography as it is in use today puts it around 2030 to 2035 in terms of when we need to have hardware that supports these things. So that's, 12 years from now, maybe, if we're lucky, which is not a lot of time if you consider the fact that hardware takes a really long time to build. Standards take a long time to develop. Consensus takes a while to build. All of these things need to start now so that we don't find ourselves behind the 8 ball when PQC finally does roll up.
Looking forward, we are starting to consider ways to support post-quantum cryptography in TPMs in the future. And that's important because as quantum computers become available, as they get large enough to solve the cryptographic problems that can't be solved by classical computers, we will need to adopt a whole new scheme of cryptography, or schemes of cryptography, because there's many ideas out there about how to do this. And none of that is in the current TPM specifications. So we're going to need to improve the specifications to provide for those capabilities over the next 5 or 10 years, because the lead time for getting things in the field is the specification has to come first, and then it takes years for the hardware manufacturers to produce the newer devices, and then for them to finally get in the field in the 15-year time horizon when maybe quantum computers are significant. We need to be working on that in the near future in order to reach that goal in time.